want to look at the Mobius function. So here the Mobius function is defined as the unique arithmetical function satisfying that mu star u is the identity. And here u is the function which is just always 1. So mu of n is 1. And this is indeed unique because we have shown that the set of arithmetical functions that are not 0 at 1 form a group. So since u is in the group, there is a unique inverse to u. So this says that the uniqueness here is in fact true. So this is general group theory. Now the theorem here says that there is a formula for the Mobius function. It's given by minus 1 to the k, if n is the product of k different primes. Now, if k is not a product of k different primes, then it's 0. Okay, so we want to prove that this function here satisfies this relation, and then by uniqueness we'll get that the Mobius function is indeed equal to that. And as you can see, this also shows that we could equally well have used this thing as the definition of the Mobius function, and then this here would be something that you would have to prove. But let's do it this way then. So let's prove that this thing convolved with u is indeed I. So we let mu star be the function over here. So it's minus 1 to the k. If n is the product of k different primes, so pi is different from pj for I not equal to j, and it's 0 otherwise. And we want to prove now that with this definition of mu star, we wish to show that mu prime convolved with u is equal to the identity. If we can prove that, then uniqueness gives us that mu prime is equal to the Mobius function, and we have proved the theorem. Okay. Now, this function over here is 1 if n is 1 and 0 otherwise. So let's distinguish those two cases. So mu prime convolved with u of 1. What is that? Well, by definition, it's the sum of the divisors of n of mu prime of d times u of n over d, and n here is 1. Now, what are the divisors of 1? Well, we're only looking at positive divisors, so the only positive divisor that 1 has is 1. So this is mu prime of 1 times u of 1 divided by 1, which is also 1. So this one is always 1. And mu prime of 1, by definition here, you should interpret this as 1 being the product of 0 different primes. So it's minus 1 to the 0. So this is minus 1 to the 0, which is indeed a 1. So mu prime star mu at 1 is 1, which agrees with what we wish to show. Now we just need to prove that if you take an n which is bigger than 1, then the convolution will give you 0. So we let n be some number p1 to the L1 times up to pk to the Lk, be some number which is bigger than 1. And let's assume that these are different primes, so pi is different from pj, or I different from j. Then we want to see what is mu prime convolved with u at n. Now again, by definition, this is just the divisors in n, mu prime of d times u of n divided by d. Now u of n divided by d is always a 1, so this one I can simply ignore because it's always a 1. Now the Mobius, no. So this side over here is only non-zero if the divisor I'm looking at is a product of k different primes. So that's how we define mu prime. So it's only non-zero if n is a product of k different primes. So this means that the divisors that will give some contributions is exactly the same as the divisors of p1 up to pk of mu prime of d. Because the divisors that are here but not here are exactly the divisors that will have some higher power of some prime, higher than 1. But for those, mu prime at that divisor is always going to give you 0. So that shows that this equality is true. Now, I want to say what these divisors are. What is a divisor? Well, 1 is a divisor. That corresponds to not taking any of these primes. And let me write that one guy as I'm choosing 0 elements out of these primes, and then the value of mu prime at 1 is 1. This is the only divisor with no prime divisors. Then there are divisors of the form equal to 1 prime. How many ways can I find a divisor which is exactly equal to 1 prime? Well, that corresponds to the number of ways I can choose 1 prime out of these k primes. So that's k choose 1 divisors. Now, mu prime on a divisor like that, i.e. a divisor which is just a prime, by definition here is -1 to the 1. So I get to multiply this by -1. Then I look at all the divisors of the form a product of 2 primes. So p times q, or p and q are one of these primes down here. Now, how many ways can I form such a divisor? Well, I have to take 2 primes out of these k primes. So I'm doing this k choose 2, I'm choosing 2 out of k. And then all these divisors have the same value of mu prime, namely -1 squared, which is 1. Then I take all the divisors that are 3 primes. I can choose those in k choose 3 ways. And the value that this function will have is -1 to the 3, which is -1. And then I continue up to the last one, which is the whole thing. So I'm choosing k out of k, and the value that that one will have is -1 to the k. So this is the value. Now by the binomial theorem, this is 1 minus 1 to the k, which of course is 0. So I have proved now that with this definition of mu prime convolved with u evaluated at n is 0 when n is strictly bigger than 1. This means that we have proved this because we have proved that for n equals 1 it's 1, and for n bigger than 1 it's 0, which is exactly the definition of I. So this proves that mu prime convolved with u is I, and by uniqueness that means that the Mobius function has this expression.